All right, let's just dive right in. Welcome to today's Explainer. We are going on a really fascinating journey today, starting directly from the everyday, mundane stuff you see in your own kitchen, all the way to structured, controlled science in the lab. We're talking about chemical reactions and equations. But hey, do me a favor. Clear your mind of any boring rote memorization you might normally associate with chemistry. Today is absolutely all about observing the dynamic universe going on right in front of us.
You know, there's this great quote by Martin H. Fisher. A dictionary is not literature, just as facts are not science. And I think this just brilliantly hits the nail on the head for our approach today. Science isn't simply a laundry list of static facts you have to forcefully memorize from some heavy textbook. Actually, scratch that. It's more like a highly active, living process of observation, questioning, and discovery. It's about seeing the how and the why behind the changes happening all around us.
To prove just how active this science really is, just think about some things you've probably encountered this week. What happens to milk if you accidentally leave it out on the counter during a hot summer day? Or an iron pan? Or maybe a nail just left outside in a super humid atmosphere? Think about grapes undergoing fermentation to become wine, or even the simple act of cooking your dinner. Consider the completely invisible process of your own body digesting that food, or respiration, literally just the act of you breathing in and out right now. In all of these everyday situations, something really fundamental happens. The initial nature and the identity of that original substance changes completely. It completely transforms.
Which naturally brings us to a really critical question. What exactly happens to the nature and identity of these substances? I mean, they don't just magically disappear. They become something entirely else. But how do we actively know a chemical reaction has actually occurred in these everyday items? A rotting grape and a rusty nail look wildly different, but underlying both of them is the exact same scientific principle. To really understand what's happening beneath the surface, we need to observe a change in a much more controlled environment.
So, let's take a look at Activity 1.1, the Magnesium Ribbon Experiment.
Okay, quick disclaimer right off the bat. This specific activity is highly combustible and absolutely requires a teacher's help and proper safety glasses. So definitely not a kitchen experiment, but it is a perfect visual tool for understanding chemical changes. Picture this setup. We have a pair of metal tongs holding the thin strip. That's our magnesium ribbon. Right below it is a burner to provide a steady flame, and underneath the action, a curved glass dish, which is called a watch glass. We are essentially setting the stage to force a reaction to happen right before our eyes.
Let me walk you through the exact procedure, step by step, just as if we were standing side by side at the lab bench. Step 1. We take about a 2-centimeter strip of that magnesium ribbon and clean it by thoroughly rubbing it with sandpaper. This just removes any surface impurities. Step 2. We grip it firmly with the tongs and bring it directly into the flame of the spirit lamp or burner. And finally, Step 3. As it burns, we carefully collect the resulting ash in the watch glass, making absolutely sure to keep that incredibly bright burning ribbon as far from our eyes as possible. And boom! When that flame hits the metal, the ribbon doesn't just quietly melt. No way. It burns with an incredibly dazzling, almost blinding bright white flame, and the solid metal strip physically changes into this fine, crumbly white powder. That powder is a brand new substance called magnesium oxide. The original magnesium has literally reacted chemically with the oxygen present in the air to create something with an entirely new identity. Let's move along and see how this builds in Activities 1.2 and 1.3, Mixing Solutions and Acids.
You know, chemical reactions don't always require a dramatic, blinding flame. Some of the most profound changes happen just by mixing things together at regular room temperature. Activity 1.2, for example, involves taking a solution of lead nitrate and mixing it with a solution of potassium iodide. Essentially, just mixing two clear liquids. Activity 1.3 is a little bit different. We take solid zinc granules and drop them into a liquid, specifically dilute hydrochloric or sulfuric acid. So I want you to think about this for a second. What visual or physical changes would you expect to witness when these specific chemicals interact?
Well, let's look at the zinc and acid reaction, because it is incredibly revealing. When you add that dilute acid to the solid zinc granules, you instantly see this evolution of gas bubbles forming all around the metal. It's fizzing, but there's also a distinct change in temperature. If you were to place your bare hand on the outside of the conical flask where this reaction is happening, you would physically feel the glass getting hot.
Which synthesizes perfectly into a huge pivotal question for us. We've seen sour milk, rusty iron, magnesium burning into white ash, and zinc bubbling and heating up in a flask of acid. So, how do we definitively know a chemical reaction has taken place? What are the universal scientific rules that tell us without a doubt that a substance has truly transformed?
Well, scientists look for 4 primary indicators: a change in state, like a solid turning into a gas, a change in color, the evolution of a gas just like those crazy bubbles we observed with the zinc and the acid, and a change in temperature, just like the heat radiating from that flask. If you observe one or more of these indicators, like the solid magnesium turning into a white powdery ash, you are witnessing a true chemical reaction. Knowing these signs is absolutely crucial because it empowers us to identify the invisible changes that are shaping the world we live in every single day.
Now, obviously, scientists need a way to document all these amazing changes. But let's be real, writing out a full descriptive sentence like magnesium reacts with oxygen to form magnesium oxide over and over again, it's incredibly tedious. That brings us to the word equation. This is a shorter, vastly simplified way to write out the full sentence describing a chemical reaction. It's basically a foundational shortcut in chemistry to keep our notes clean, focused, and highly structured.
But listen, word equations are really just the beginning of the journey. I want to leave you with a slightly provocative thought to chew on. If word equations are a shorter way to write things out, how can we write these reactions in a secret universal scientific code? A code that uses symbols and numbers so that a chemist literally anywhere in the world can understand exactly what happened in your lab. Think about how we might translate those words into symbols. Because that is exactly the code we are going to crack in our next explainer. Thanks so much for joining me today. Keep observing the world around you and stay curious.